What if the greatest barrier to reaching the stars is not distance but a misunderstanding? What if the wall we have been pushing against for a century exists only because we have been asking the wrong question? Right now, in quiet laboratories and on dusty blackboards, a small group of physicists is exploring an idea so strange that most of their colleagues refuse to take it seriously. They are not trying to make objects move faster. They are trying to make movement itself irrelevant. And the mathematics, against all expectation, appears to be on their side. We need to begin with something that sounds simple, but contains a profound mystery. Space is not what you think it is. When you look across a room, you perceive emptiness between yourself and the far wall. Air fills that gap, of course, but remove the air and you would still sense distance. That distance feels fundamental. It seems like a fixed stage on which objects exist and events unfold. Physics spent centuries treating space exactly this way, as a passive container, a backdrop, a void measured in meters and miles. This intuition is wrong. Space is a thing. It has properties. It responds to its contents. It bends under the influence of mass and energy. It can stretch, compress, ripple, and flow. Most remarkably, space can move. Not objects moving through space, but space itself carrying objects along like a river carries a leaf. This single insight, buried in equations written over 100 years ago, contains the seed of everything we are about to explore. Because if space can move, then the speed limit we have accepted as absolute might apply only to motion through space, not to the motion of space itself. The distinction sounds subtle. It changes everything. Consider what happens when you drive a car on a highway. Your speedometer might read 60 miles per hour. That measurement describes your motion relative to the road beneath you. But what if the road itself were moving? What if the entire highway, pavement and all, were sliding forward at 100 miles per hour? Your speedometer would still read 60, but relative to the landscape beyond the highway, you would be traveling at 160. You have not violated any speed limit. You have simply been carried by something that has no limit. Space operates this way. The universe is expanding, and distant galaxies are receding from us at rates that exceed what we call the speed of light. They are not moving through space faster than light. They are being carried by space that is stretching between us and them. No law is violated. No physics breaks down. The galaxies simply ride an expanding medium that obeys different rules than objects moving within it. If expansion can carry galaxies faster than light, could deliberate manipulation of space carry a spacecraft the same way? This question has haunted theoretical physics for decades. For most of that time, the answer seemed to be a firm no. The energy required to deliberately move space appeared so astronomical, so far beyond any conceivable technology, that the question was academic. Interesting for blackboard discussions, irrelevant for engineering. That assessment is changing. To understand why, we need to look at what has happened in physics over the past 30 years. Not the headline discoveries, the black hole images and gravitational wave detections, but the quieter theoretical work that most people never hear about. This work has gradually revealed that the energy barriers we assumed were fundamental might instead be artifacts of oversimplified calculations. The walls might be lower than we thought, perhaps dramatically lower. But let us not get ahead of ourselves. Before we can appreciate what the new research shows, we need to understand the problem it addresses. The speed of light is not merely a speed, it is a structural feature of the universe. When Einstein developed his theories of relativity, he was not simply cataloging how fast things can move. He was uncovering the deep geometry of reality. Space and time, he showed, are not separate. They are woven together into a unified fabric called space-time. This fabric has a specific structure, and that structure determines what is and is not possible. Within this structure, the speed of light plays a peculiar role. It is the conversion factor between space and time. It defines how distance and duration relate to each other. It sets the maximum rate at which cause can precede effect. Violating the light speed limit would not just be difficult, it would require breaking the logical structure of events, allowing consequences to happen before their causes. This is why physicists take the limit so seriously. It is not an arbitrary rule that nature chose. It is woven into the foundation of how events relate to each other. For objects moving through space-time, this limit appears absolute. The faster something moves, the more energy it requires to accelerate further. As it approaches light speed, the energy requirement grows without bound. You can get arbitrarily close, but you can never reach the limit, let alone exceed it. Every experiment ever conducted confirms this. Particle accelerators push protons to within a hair's breadth of light speed, and the protons behave exactly as the equations predict. They gain energy. Their internal clocks slow down. They resist further acceleration with increasing stubbornness. The math works perfectly, so the barrier is real. For conventional motion, for objects pushing through space under their own power, the speed of light is an unbreakable wall. But here is where the story takes its crucial turn. The equations that describe space-time geometry, the equations of general relativity, permit something strange. They allow configurations where space itself is in motion. They describe scenarios where a region of normal, flat space is surrounded by a shell of extreme curvature, and the whole arrangement moves as a unit. Inside such a configuration, nothing special happens. Objects float normally. Physics proceeds as usual. No speed limits are violated locally. But the configuration as a whole, the bubble of normal space wrapped in distortion, can travel across the cosmos at any speed whatsoever. The objects inside are not moving through space faster than light. Space is moving them. This is not science fiction. It is what the equations say. The question has always been whether the equations describe something that could actually exist, or whether they are merely mathematical curiosities with no physical counterpart. That question remains open, but the evidence is shifting. To create a moving bubble of space-time, you would need to manipulate the geometry around it. You would need to compress space in front and expand space behind, creating an asymmetry that generates motion. The mathematics of this is well understood. The challenge is physical. What would create such distortions? In ordinary circumstances, mass and energy curve space-time. Stars bend the geometry around them. Black holes create extreme curvature. But this is passive curvature, a response to matter that exists. A warp drive would require active curvature, geometry created deliberately and moved at will. The only way to do this, according to most analyses, is with something called negative energy density. Energy, in everyday experience, is always positive. Kinetic energy from motion, thermal energy from heat. chemical energy stored in bonds. Even mass represents a form of positive energy, as Einstein's famous equation reveals. The baseline, the ground state, is zero. You cannot go below zero, except that quantum mechanics says otherwise. At scales far smaller than atoms, the vacuum of space is not truly empty. It seethes with activity. Fields fluctuate constantly. Virtual particles appear and disappear. Energy borrows from the future and repays it an instant later. This quantum vacuum has a baseline energy level, and under certain conditions, you can create regions where the energy density drops below this baseline. Such regions exhibit negative energy density. Not negative energy in absolute terms, but energy lower than the surrounding vacuum. For the purposes of space-time curvature, this distinction does not matter. Regions with less energy than the vacuum curve space in the opposite direction from normal matter. They push where mass pulls. They expand where mass contracts. This is exactly what a warp bubble requires. The first rigorous description of such a bubble came from a physicist named Miguel Alcubierre in 1994. His work showed mathematically that a shell of negative energy density surrounding a flat region could create the necessary space-time distortion. The bubble would move, carrying its contents, without anything inside ever exceeding local speed limits. The physics was sound. The engineering was impossible. When Alcubierre calculated how much negative energy his bubble would require, the result was absurd. More energy than exists in the observable universe, except with a minus sign. This was not a call for better engineering. It was a statement that the concept, while mathematically valid, had no practical application. For most physicists, this ended the discussion. Warp drive became a curiosity, something to mention in popular science books, but not worth serious research. The numbers simply did not work. But mathematics is slippery, and assumptions hide in equations. Alcubierre had chosen a specific geometry for his bubble, one that was mathematically simple but perhaps not optimal. The question arose whether other geometries might require less energy. Over the following decades, researchers explored this question, and they found that the answer was yes. By adjusting the shape of the bubble, the thickness of the boundary, and the rate of transition between normal space and distorted space, theorists discovered they could reduce the energy requirements significantly. Not to achievable levels, but from universe-scale impossibility to merely astronomical impossibility. This might seem like small progress, but in physics, reducing an infinite barrier to a finite one is meaningful. Then came more surprising developments. Some researchers found geometries that might not require negative energy at all. By using different configurations of ordinary positive energy, arranged in specific patterns, they showed that warp-like effects might be achievable without exotic matter. The configurations were complex, the energy still enormous, but the fundamental requirement for negative energy was no longer absolute. Others approached the problem from a different direction. Instead of asking how to minimize energy for a spacecraft-sized bubble, they asked what scale of effect might be achievable with laboratory-level energies. The answer was interesting. Microscopic effects, far too small to transport anything useful, might be possible with currently imaginable technologies. Why does this matter? Because demonstrating any warp effect at any scale would transform the research landscape. It would move warp physics from theoretical speculation to experimental science. It would attract funding, talent, and serious attention. This is where current research focuses. Not on building starships, but on detecting whether space-time can be deliberately warped in ways the equations predict. Let us examine what such experiments might involve. The most obvious approach uses the Casimir effect, a phenomenon where quantum vacuum fluctuations create measurable forces between closely spaced surfaces. When two conducting plates are brought extremely close together, the vacuum between them contains fewer fluctuation modes than the vacuum outside. This creates a pressure difference, pushing the plates together. The effect is real and has been measured with high precision. It demonstrates that the quantum vacuum has structure, that its energy density can be modified by boundary conditions, and that these modifications produce physical consequences. Some researchers have proposed that dynamic variations of the Casimir geometry might create larger effects. If the plates move or oscillate, the vacuum energy between them changes in time. Under certain conditions, this might produce detectable space-time disturbances. The effects would be tiny. No one expects to see macroscopic warp bubbles emerge from laboratory apparatus. But detecting any deliberate space-time modification would be significant. Another approach involves high-intensity electromagnetic fields. When fields become sufficiently strong, they interact with the quantum vacuum in ways that might produce geometric effects. Extreme laser pulses, magnetic fields near the limits of material tolerance, and configurations designed to maximize field gradients are all being explored as potential probes of vacuum structure. The connection to warp physics is indirect but real. If we can understand how fields interact with the vacuum, we might learn to manipulate vacuum properties more effectively. And vacuum properties at a deep level determine space-time geometry. A third line of research focuses on theoretical refinement. The calculations that produce astronomical energy requirements make assumptions. They assume specific geometries, specific material properties, specific configurations. Challenging these assumptions has already reduced energy estimates significantly. Further refinement might reduce them more. Some physicists believe that a full theory of quantum gravity, which we do not yet possess, might reveal mechanisms for space-time manipulation that current physics cannot predict. Our understanding of how quantum mechanics and gravity combine is incomplete. The complete theory, when we have it, might contain surprises. This is speculative, of course. Counting on unknown physics to solve known problems is not a reliable strategy. But it reminds us that our current knowledge is incomplete, and incomplete knowledge sometimes yields unexpected possibilities. Beyond laboratory experiments, there is another source of potential evidence: the cosmos itself. If warp drive is possible, and if the universe is old enough and large enough, then perhaps some civilization somewhere has developed it. Warp bubbles moving through space might leave traces. They might interact with interstellar matter, producing radiation. They might generate gravitational waves with distinctive signatures. They might create observable effects that, if we knew what to look for, would stand out against natural backgrounds. Gravitational wave detectors have reached extraordinary sensitivity. They routinely detect ripples in space-time from events billions of light-years away. In principle, they might detect artificial space-time manipulations if such manipulations produce recognizable signals. Some researchers have proposed searches for anomalous gravitational wave signatures that might indicate artificial origins. These proposals remain speculative. We do not know what a warp signature would look like. We do not know if any civilizations have warp capability. We do not know if detectable signals would be produced, but the search is cheap compared to the potential payoff. If we detected evidence of artificial space-time manipulation anywhere in the cosmos, it would prove the concept is possible. That proof would be invaluable guidance for our own research efforts. The absence of detection also carries information, though less decisive. The universe is vast. Our detectors cover only a tiny fraction of it. Warp-capable civilizations might be rare. Detectable signals might be infrequent. Absence of evidence is not evidence of absence, but extended absence would constrain some scenarios. Let us step back and consider what we have established. The physics of space-time permits configurations that would allow faster-than-light travel without violating the light-speed barrier. These configurations would move space rather than moving through space. The mathematics is sound. The theoretical framework is solid. The challenge is engineering. Creating the required space-time distortions demands manipulating the quantum vacuum in ways we do not currently understand. The energy requirements, while they have been reduced from impossible to merely extreme, remain far beyond current capability. Research continues on multiple fronts. Theoretical refinement seeks to reduce energy estimates further. Laboratory experiments probe whether any space-time manipulation is achievable at small scales. Observational programs look for evidence that warp effects exist somewhere in the cosmos. The outcome is uncertain. Some barriers in physics are fundamental, built into the structure of reality, never to be overcome. Others are practical, difficult, but not impossible, yielding eventually to persistence and ingenuity. We do not yet know which category contains warp drive, but the research itself is valuable, regardless of outcome. Physics advances by pushing against boundaries, testing limits, exploring possibilities. Even negative results, demonstrations that certain approaches do not work, contribute to understanding. And the history of physics contains enough surprises to counsel humility about declaring anything permanently impossible. Consider what happened with black holes. When the equations of general relativity were first solved completely by Carl Schwarzschild in 1916, they revealed solutions describing regions where gravity became so intense that nothing could escape. These solutions seemed pathological. Einstein himself doubted they corresponded to anything real. For decades, most physicists dismissed them as mathematical artifacts with no physical meaning. Then evidence accumulated. Strange objects were detected that behaved as the equations predicted. Theoretical understanding deepened. What seemed impossible became first plausible, then accepted, then directly observed. We now have images of black holes, confirmation that these mathematical curiosities are indeed real. The path from equation to acceptance took most of a century. The path for warp physics might be similar, or it might be shorter, or it might lead nowhere. We cannot know in advance. What we can do is follow the evidence, refine the theory, conduct the experiments, and remain open to wherever the results lead. Let us examine some of the specific obstacles that warp drive research must overcome. The most fundamental is energy. Even optimized warp geometries require energy densities far beyond anything we can currently produce. The energy must be negative, which adds another layer of difficulty, and it must be configured precisely, shaped into specific geometries that create the desired space-time distortion. Scaling presents particular challenges. Laboratory demonstrations of negative energy effects involve tiny regions, nanometers at most. Warp bubbles large enough to enclose spacecraft would need to be meters or kilometers across. Scaling up by factors of billions or trillions is not simply more of the same. New physics might emerge at larger scales that prevents the effects we observe at small scales. Stability is another concern. Theoretical analyses suggest that some warp geometries might be unstable, collapsing or exploding rather than maintaining their shape. A practical warp drive would need to sustain its geometry for the duration of a journey, potentially weeks or months or years. Understanding what makes warp configurations stable is an active area of research. Control presents its own difficulties. Creating a warp bubble is one challenge. Steering it, accelerating it, decelerating it, bringing it safely to rest, these are additional challenges that multiply the complexity. The bubble would need responsive control, the ability to adjust course based on observations. How you communicate with a system that is functionally outside normal space-time is not obvious. Safety considerations are severe. A warp bubble moving through space would interact with any matter in its path. Interstellar space is not truly empty. Gas, dust, and occasional larger objects drift between the stars. What happens when a warp bubble encounters this material? Some analyses suggest the material would accumulate at the bubble boundary, potentially releasing enormous energy when the bubble stopped. Others suggest different outcomes. The physics is not fully understood. These obstacles are formidable. They might be insurmountable, or they might yield to approaches we have not yet imagined. One reason for cautious optimism is that the obstacles are engineering obstacles rather than physics obstacles. Physics determines what is possible. Engineering determines what we can build. If physics permits warp drive, then engineering will eventually find a way, given sufficient time and resources. The key qualifier is whether physics permits it. This remains uncertain. General relativity permits it, but general relativity might not be complete. Quantum effects might introduce constraints that classical gravity does not predict. A full theory of quantum gravity, which we do not yet have, might resolve this uncertainty. Some physicists argue that the universe has protection mechanisms that prevent pathological configurations. The chronology protection conjecture, proposed by Stephen Hawking, suggests that nature prevents arrangements that would allow time travel or violations of causality. If warp drives would enable such violations, some unknown physics might block their formation. The argument is plausible but unproven. We do not know if protection mechanisms exist, and if they do, what form they take. Until we understand quantum gravity better, this question will remain open. Other physicists take a more optimistic view. They note that every previous prediction of impossibility based on incomplete physics has eventually been revised. They suggest that assuming impossibility is historically unjustified, that we should remain agnostic until we have complete knowledge. Both positions are defensible. The honest answer is that we do not know. What we do know is that research continues, understanding deepens, and possibilities that seemed closed sometimes reopen. Physics has surprised us before. It might surprise us again. Let us consider what the world might look like if warp drive, or something like it, eventually proves achievable. The most immediate consequence would be the opening of interstellar space to human exploration. Stars that currently seem unreachable would become accessible. Journeys measured in lifetimes would shrink to journeys measured in years or months or weeks, depending on how effective the technology proved. The number of potentially habitable worlds within reach would explode. Current estimates suggest that billions of Earth-like planets exist in our galaxy alone. Most are far too distant for conventional spacecraft to reach in any practical time frame. Warp-capable vessels would change this calculation fundamentally. Humanity would face choices we have never confronted. Which worlds to visit first? How to distribute access to the technology? What rights do settlers have to new worlds? How to govern communities spread across light years? These questions have been debated in science fiction, but they would become practical policy matters requiring real decisions. The economic implications would be profound. Resources available on other worlds, in asteroid belts, and in interstellar space would dwarf anything accessible from Earth alone. Mining, manufacturing, and energy production could expand to scales currently unimaginable. The entire concept of scarcity might change when resources become effectively unlimited. Scientific discovery would accelerate dramatically. Instead of studying distant phenomena through telescopes, we could investigate them directly. Alien ecosystems, if they exist, could be examined in person. Stellar interiors, black hole environments, neutron star surfaces, all could become subjects of close observation rather than distant inference. The question of other intelligent life would become urgent. If we can reach other star systems, we might encounter civilizations or their remains. Contact with alien intelligence or discovery of long-dead civilizations would transform human philosophy, religion, and self-understanding in ways we cannot predict. These possibilities feel remote. Current technology is nowhere near capable of achieving them. Centuries might pass before practical warp drive, if possible at all, reaches the engineering stage. But futures have a way of arriving faster than expected. A century ago, human flight was a novelty. 50 years ago, computers filled rooms and served narrow purposes. 20 years ago, smartphones did not exist. The pace of transformation is difficult to predict, and transformations once begun often accelerate. Warp drive might follow this pattern, or it might not. Some technologies mature quickly, others take centuries. Some prove permanently impossible, despite initial promise. What we can say is that the research direction is clear. Reduce energy requirements, demonstrate small-scale effects, understand the quantum vacuum better. These goals are achievable with current or near-term capabilities. Progress on them would clarify whether larger goals are realistic. The timeline is uncertain, but not necessarily long. Major breakthroughs sometimes come quickly, once the right approach is found. Einstein developed special relativity in weeks once his thinking crystallized. Quantum mechanics emerged rapidly once the key insights appeared. Warp physics might experience similar acceleration if someone finds the conceptual key, or it might take centuries. Some problems resist solution despite enormous effort. Practical fusion power has been 20 years away for 70 years. Strong artificial intelligence has been predicted for decades and remains elusive. Warp drive might join this category of problems that are harder than they appear. The uncertainty itself is significant. We are not working on a well-understood engineering project with clear milestones. We are exploring the boundaries of physics, where surprises are possible in both directions. Let us turn to some of the specific concepts that current research explores. One important area involves the quantum vacuum itself. Understanding vacuum structure better might reveal mechanisms for manipulation that we currently overlook. The vacuum is remarkably rich. It contains fluctuating fields at every point in space. These fluctuations have measurable consequences, from the Casimir effect to subtle shifts in atomic energy levels. The vacuum interacts with matter and energy in complex ways that we are still mapping. One intriguing property is that vacuum energy appears to be enormous when calculated from quantum field theory. The predicted energy density vastly exceeds what we observe cosmologically. This discrepancy, called the cosmological constant problem, is one of the deepest unsolved puzzles in physics. The resolution might involve physics we do not understand, physics that could have implications for vacuum manipulation. If the vacuum somehow cancels most of its energy through mechanisms we have not identified, understanding those mechanisms might reveal new capabilities. This is speculative, but it illustrates how incomplete knowledge leaves room for surprises. The vacuum is strange. Strange things sometimes turn out to be useful. Another area of interest involves exotic states of matter. Under extreme conditions, matter behaves in ways that normal experience does not prepare us for. Neutron stars contain matter so dense that atomic nuclei merge into a continuous fluid of neutrons. The cores might contain even stranger phases, quark matter, or exotic particles that do not exist under ordinary conditions. These extreme states exhibit properties that differ radically from normal matter. Black holes represent the ultimate extreme, matter compressed until space-time itself breaks down. What happens inside a black hole, beyond the event horizon, remains mysterious. General relativity predicts a singularity, a point of infinite density. This prediction is probably wrong, replaced by something from quantum gravity that we do not yet understand. Studying extreme matter and extreme gravity might reveal principles applicable to space-time manipulation. The connection is speculative, but extreme conditions often expose physics that mild conditions conceal. A related area involves high-energy physics and the fundamental forces. The strong force that binds atomic nuclei, the weak force that governs radioactive decay, the electromagnetic force that controls chemistry, and gravity that shapes cosmic structure. These four forces might unify at extremely high energies. Grand unified theories and string theory predict that the forces we observe are different manifestations of a single underlying force. At energies far beyond current accelerators, this unity might become apparent. And with unity might come capabilities we cannot currently access. This is highly speculative territory. The energies required for unification are far beyond any technology we can imagine. But understanding the deep structure of forces might reveal leverage points, ways to achieve effects that brute force cannot produce. Quantum entanglement offers another direction to consider. Entangled particles exhibit correlations that persist across distances. Correlations that seem to ignore the limitations of signal speed. When you measure one entangled particle, the result is instantly correlated with what you would find measuring its partner, no matter how far apart they are. This does not actually allow faster-than-light communication. The correlations are statistical, revealing their pattern only when results from both measurements are compared through ordinary channels. No usable information travels faster than light. But entanglement reveals that space-time relationships are more subtle than simple distance suggests. Entangled particles have a connection that transcends separation in some sense. Understanding this better might reveal something about space-time structure that bears on manipulation possibilities. Again, the connection to warp physics is speculative, but entanglement demonstrates that our intuitions about space and locality are incomplete. Incomplete intuitions sometimes conceal possibilities. Let us consider the work of specific research groups pushing these boundaries. Several academic institutions maintain active programs in advanced propulsion physics. These programs are small compared to mainstream physics efforts, but they exist and produce peer-reviewed research. NASA has supported advanced propulsion research intermittently over the years. The Breakthrough Propulsion Physics program, which ran from 1996 to 2002, explored exotic concepts including space-time manipulation. Though the program ended, interest persists among some NASA researchers. Private organizations have emerged to fund long-term breakthrough research. These organizations, supported by wealthy individuals with patience for speculative investment, provide resources for work that government programs cannot easily support. International collaborations exist informally. Researchers in this field know each other, share preprints, attend specialized conferences, and build on each other's work. The community is small enough that significant results circulate quickly. The pace of publication has increased in recent years. Theoretical papers, refining energy estimates, exploring new geometries, analyzing quantum vacuum effects, appear regularly in physics journals. The field is active and growing, even if it remains marginal within physics as a whole. Laboratory experiments are more limited. The effects being sought are tiny, requiring extraordinary sensitivity to detect. Equipment costs are significant. Securing funding and institutional support for speculative experiments is difficult. Progress is slower than theoretical work. But experiments do occur. Sensitive measurements of vacuum effects, tests of unusual electromagnetic configurations, searches for anomalous forces. These efforts accumulate data that constrains or supports theoretical predictions. The overall picture is of a field in early development. Theoretical understanding advances. Experimental capabilities improve gradually. The gap between theory and experiment remains large but is not obviously unbridgeable. Where will this lead? Predictions are hazardous in science, especially for speculative areas. But we can identify what success would require and assess rough plausibility. For warp drive to become practical, several things would need to happen. First, theoretical understanding would need to clarify whether the concept is physically possible at useful scales. This requires progress on quantum gravity, better understanding of vacuum structure, and refinement of warp geometry calculations. Second, laboratory demonstrations would need to confirm that space-time can be deliberately manipulated. Even tiny effects would validate the theoretical framework and attract resources for larger efforts. Third, scaling would need to prove feasible. Effects achievable at small scales would need to extend to larger scales without encountering fundamental barriers. Fourth, engineering solutions would need to emerge for control, stability, safety, and practical operation. Fifth, economic and social infrastructure would need to develop to support construction and operation of warp-capable vessels. Each step faces obstacles. Each might prove impossible, but none is obviously impossible based on current knowledge. The chain from here to there is long and uncertain, but it is not clearly broken. Timescales are pure speculation. If everything goes well, if theoretical breakthroughs come quickly, and scale-up proves straightforward, perhaps a century could see significant progress. If obstacles prove stubborn, millennia might pass with a little advance. If the concept is fundamentally impossible, no amount of time will achieve it. The honest answer is that we do not know. We can hope, speculate, and work, but certainty is not available. Let us step back and consider why this matters, beyond the practical question of whether we can build starships. The warp drive question touches something deep about human nature and human destiny. We are a species that explores. From the African savanna to every continent, across oceans to new lands, into the sky and beyond Earth, we push boundaries. This drive is not merely practical. It is something closer to spiritual, a need to discover what lies beyond the known. The stars represent the ultimate frontier. Everything else we might explore exists within our solar system, a tiny bubble around one ordinary star. The galaxy contains hundreds of billions of stars, and the observable universe contains hundreds of billions of galaxies. The scale of what remains unknown is staggering. If we are permanently confined to one solar system, this vast cosmos becomes forever unreachable. We can observe it, but never visit it. We can wonder about other worlds, but never walk on them. We can speculate about other life, but never encounter it. This confinement would not end humanity. We could build fulfilling civilizations within the solar system. We could achieve great things without ever leaving our stellar neighborhood. But something would be lost. A possibility foreclosed. A door permanently closed. If warp drive proves possible, that door opens. The galaxy becomes accessible, at least in principle. The cosmos becomes a place we can explore rather than merely observe. The future expands from centuries to billions of years, from one star to hundreds of billions. The difference matters philosophically, even if practical warp drive lies far in the future. Knowing that expansion is possible changes how we think about ourselves and our place in the universe. Knowing that we might someday reach the stars gives the present different meaning. This is why warp drive research attracts interest beyond its immediate practical prospects. It addresses a question about what humanity can become, about whether our future is local or cosmic. The question might not be answered in our lifetimes. It might not be answered for centuries, but it will be answered eventually, one way or another. Either physics permits what we seek, or it does not. Either we find a way, or we do not. The outcome matters. The attempt matters regardless of outcome. Let us examine some of the philosophical implications more carefully. If warp drive proves possible, it raises questions about how common such technology might be in the cosmos. The universe is old. If warp physics works, civilizations elsewhere have had billions of years to develop it. Where are they? This is a version of the Fermi paradox, the observation that we see no obvious signs of extraterrestrial civilization, despite the apparent probability that such civilizations exist. Warp capability would make the paradox sharper. Civilizations that could cross the galaxy should have had time to visit every star, including ours. Their absence requires explanation. Various explanations have been proposed. Perhaps warp drive is not possible after all. Perhaps civilizations rarely develop it, even when physics permits. Perhaps they are present, but undetected. Perhaps they are avoiding contact. Perhaps something regularly destroys civilizations before they reach this capability. None of these explanations is satisfying. The puzzle remains. If we develop warp capability ourselves, we would have new ways to investigate. We could search for traces of other civilizations, visit promising star systems, and perhaps find answers to this deep question. Another philosophical implication involves human identity. A humanity spread across many star systems would diversify in ways we can barely imagine. Isolated colonies would develop distinct cultures, languages, and perhaps even distinct biologies over long timescales. What holds such dispersed humanity together? What makes them still human? These questions echo past human experience. Dispersal across continents produced the diversity of cultures we observe today. Further dispersal across stars would produce far greater diversity. Whether this is something to celebrate or lament depends on values that different people hold differently. Questions of ethics and governance would multiply. Who decides which worlds to colonize? What obligations do we have to indigenous life if we find it? How do we prevent conflicts between distant colonies? How do we ensure that benefits and risks are distributed fairly? We have frameworks for addressing such questions on Earth. Imperfect, but functional. Extending these frameworks to interstellar scales would challenge them severely. New thinking would be required. None of these implications argue against pursuing warp capability. They simply remind us that technology does not solve problems by itself. It creates new possibilities, and with new possibilities come new challenges. Humanity would need to grow in wisdom alongside growing in capability. Let us consider the role of individual effort in this endeavor. Large-scale projects often obscure the importance of individual contributions. Warp drive research involves institutions, funding agencies, and collaborative teams. But breakthroughs ultimately come from individual minds having individual insights. The history of physics is full of examples. Einstein working alone on relativity, Dirac finding his equation for the electron, Hawking analyzing black hole radiation. Individual creativity drives progress even in collaborative fields. Someone working today, perhaps a graduate student or young professor or amateur theorist, might have the key insight that transforms warp physics. The breakthrough could come from any direction, from mainstream physics or from unconventional approaches. This possibility gives the enterprise a personal dimension. Not everyone can contribute equally, of course. The mathematics is demanding, the physics is subtle. The experimental work requires resources few possess. But contributions are possible at many levels, from fundamental theory to engineering analysis to philosophical reflection. The field is small enough that significant contributions are noticed. A paper that genuinely advances understanding will find an audience. An experiment that produces unexpected results will attract attention. The barriers to entry, while real, are not insurmountable for those with talent and persistence. Whether or not you personally work on warp physics, understanding what is at stake enriches appreciation of the endeavor. Science benefits from an informed public that values fundamental research, even when practical applications are distant. Let us return to the core scientific questions and summarize what we know and do not know. We know that general relativity permits space-time configurations that would allow effectively faster-than-light travel. The mathematics is solid. The configurations involve regions of flat space surrounded by distortions that create movement. Objects inside would not violate local speed limits, but would be carried by the motion of space itself. We know that creating such configurations would require manipulating space-time geometry deliberately. The most studied approaches involve negative energy density, which would be produced by quantum vacuum effects. The energy requirements have been reduced through theoretical work, but remain far beyond current capability. We know that laboratory demonstrations of related effects are possible at tiny scales. The Casimir effect confirms that vacuum energy density can be modified by boundary conditions. Whether larger scale manipulation is feasible remains unknown. We do not know whether quantum gravity imposes constraints that would forbid warp configurations at useful scales. Our understanding of quantum gravity is incomplete. Until it improves, fundamental possibility remains uncertain. We do not know whether practical energy sources for warp drive exist. Current approaches require energies vastly exceeding anything we can produce. Unknown physics might provide more efficient approaches or might not. We do not know whether engineering solutions exist for control, stability, and safety. These problems have received less attention than the fundamental physics, but they would need to be solved for any practical application. We do not know whether any other civilization has achieved warp capability. The absence of obvious evidence is consistent with many hypotheses. Detection of alien warp activity would transform our understanding. This summary reveals how much remains uncertain. Optimism and pessimism are both defensible positions. The honest answer to whether warp drive is possible is that we do not yet know. What we can say is that the question is meaningful, the research is active, and progress is being made. Whether that progress leads eventually to starships or to deeper understanding of physics without practical applications remains to be seen. The journey of exploration continues. Each experiment, each theoretical paper, each discussion and debate moves us incrementally toward answers. The pace may be slow, the ultimate destination uncertain, but the direction is clear. We are reaching toward the stars. Whether we can grasp them remains unknown, but the reaching itself is worthy. The universe is vast beyond comprehension. Light has been traveling for 13 billion years and has not crossed it. Distances that numb the mind separate us from wonders we can barely imagine. Black holes devouring stars, galaxies colliding in slow-motion catastrophe, planets with conditions utterly unlike Earth, perhaps harboring life forms we cannot conceive. All of this exists, all of it real, all of it separated from us by distances that conventional physics says we can never bridge in human timescales. But physics is not finished. Our understanding is incomplete. The equations that seem to confine us also contain hints of escape. The vacuum that appears empty seethes with energy. Space that seems passive can bend and flow. Somewhere in these hints, in these strange properties of reality, there might be a path. A way to move without moving, to cross distances without traversing them, to reach the unreachable through cleverness rather than brute force. Finding that path, if it exists, is the work of generations. The scientists laboring today in obscure laboratories, writing papers that few will read, running experiments that might fail, they are the pioneers. Their work may not bear fruit in their lifetimes, but without them, progress would not happen at all, and perhaps, eventually, their successors will succeed. Perhaps humanity will spread among the stars. Perhaps we will encounter other minds that have made the same journey. Perhaps the universe will become not just a vista to admire, but a home to inhabit. Or perhaps not. Perhaps the barriers are real and permanent. Perhaps we will remain confined, watching the cosmos from our single vantage point, never touching what we see. Either outcome would reveal something profound about the universe and our place in it. Either outcome would deserve our attention and our thought. For now, we live in the uncertainty between these possibilities. We do not know which future awaits. We cannot know until the research is done, the experiments are run, the questions are answered. But we can appreciate the question itself. We can marvel that creatures evolved on a small planet around an ordinary star can even ask whether the stars are reachable. We can take pride in the persistence and creativity that drives us to keep asking, keep exploring, keep pushing against limits. The warp drive might work, or it might not. But the attempt to understand whether it can work is itself an achievement. It represents humanity at its best, curious and determined, and unwilling to accept limits without testing them. Whatever the answer turns out to be, the asking is worthy. The cosmos awaits. Whether we can reach it remains to be seen. But we are trying. And in the trying, we discover who we are. The laboratories continue their work. The theorists refine their equations. The dreamers imagine possibilities. And somewhere, in the equations and experiments and dreams, the answer waits. We will find it eventually. One way or another, we will find it. Until then, we keep looking up, keep wondering, keep reaching. Because that is what we do. That is what we have always done. And that is what we will always do, as long as stars shine in the night sky and humans exist to wonder at them. The future is unwritten. The path is unclear. But the journey has begun, and it will not end until the question is answered. What lies between the stars? Can we ever cross the void? Is the universe our home or our prison? We do not know yet, but we are working to find out. And that work continues, day by day, experiment by experiment, equation by equation, moving us ever closer to an answer that will shape the future of our species. The stars are waiting. Whether we can reach them is the question. The research continues. The answer will come. And when it does, everything changes. Or perhaps nothing changes. And we learn to accept our confinement with grace. Either way, we will know. And knowing, whatever we learn, is better than not knowing. This is why the research matters. This is why the questions matter. This is why, even when the answers seem impossibly distant, we keep asking. Because that is what humans do. We ask, we seek, we reach. And sometimes, against all odds, we find what we are reaching for. The stars are far, but far is not forever. Not necessarily. Not if the physics permits what we hope. We will see. In time, we will see. Until then, the work continues. The questions remain open. The possibilities remain alive. And somewhere in the vastness of space, the answers wait for those persistent enough to find them. The work continues in ways that most people never see. Consider what happens inside a physics laboratory dedicated to fundamental research. There are no dramatic moments, no sudden revelations accompanied by orchestral swells. There is only the slow accumulation of data, the careful checking of instruments, the tedious refinement of experimental protocols. A researcher might spend months preparing for a measurement that takes seconds to perform. The result might be null, showing nothing unusual. adding one more data point to a growing collection of non-discoveries. This is how science actually works. Not through breakthroughs, but through the patient elimination of possibilities. Each null result closes a door, narrows the search space, guides future efforts toward more promising directions. The breakthrough, when it comes, arrives on the foundation of 1,000 failed experiments. Warp drive research follows this pattern. The headlines focus on theoretical papers proposing new geometries or reduced energy requirements. The actual work involves painstaking measurements of forces between microscopic surfaces, careful calibrations of sensitive instruments, and endless troubleshooting of equipment that refuses to behave as expected. But something interesting has emerged from this slow work. Over the past decade, several research groups have reported anomalous results in experiments probing vacuum effects. The anomalies are small, at the edge of detectability, and their interpretation is contested. But they exist. They appear in the data. They demand explanation. One class of anomalies involves the Casimir force itself. The standard calculation predicts specific force values for specific geometries. Most experiments confirm these predictions. But some configurations produce forces that differ slightly from expectation. The differences are tiny, percentage-level deviations that could easily be dismissed as experimental error. Except that similar deviations appear in multiple independent experiments. Different laboratories, different equipment, different researchers, and yet the pattern persists. Either all these experiments share a common systematic error, or something about the vacuum differs from standard calculations. If the vacuum differs, the implications could be significant. The Casimir force depends on the structure of vacuum fluctuations. If those fluctuations behave differently than theory predicts, even slightly, the difference might reveal physics we do not understand. And physics we do not understand sometimes contains possibilities we have not imagined. This is why anomalies matter in fundamental research. They are cracks in the edifice of current knowledge, hints that something remains to be discovered. Most anomalies eventually find mundane explanations, errors in analysis, or uncontrolled variables in experiments. But occasionally, an anomaly points toward genuinely new physics. The vacuum anomalies currently under investigation might fall into either category. We do not know yet. The experiments continue, the data accumulates, and eventually, the pattern will become clear. Another area generating unexpected results involves what researchers call dynamic Casimir effects. The standard Casimir effect is static. Two surfaces held at fixed separation experience a steady force. But what happens if the surfaces move? What if you oscillate a mirror at very high frequencies? Theory predicts that the changing boundary conditions should create real particles from the vacuum, a phenomenon called the dynamical Casimir effect. This effect was first observed in 2011, using superconducting circuits rather than physical mirrors. The observation confirmed that vacuum fluctuations can be converted into real photons by changing boundary conditions rapidly enough. The vacuum is not merely a background, it participates in physical processes. Recent experiments have pushed further. By using more sophisticated oscillation patterns, researchers have explored how different types of motion affect vacuum particle creation. Some results match predictions closely. Others show deviations that remain unexplained. The deviations are interesting because they might indicate that vacuum response to boundary changes is more complex than current theory captures. If the vacuum can be stimulated in unexpected ways, if its response to perturbation contains surprises, then our picture of vacuum structure is incomplete. An incomplete picture means missing knowledge. Missing knowledge means potential capabilities we have not recognized. This chain of reasoning is speculative, but not unreasonable. The history of physics contains many examples where anomalous observations eventually led to new understanding and new capabilities. Radioactivity was an anomaly before it was understood. The photoelectric effect was anomalous before Einstein explained it. The cosmic microwave background was unexpected noise before it was recognized as evidence for the Big Bang. Anomalies deserve attention. They are where new physics hides. Let us consider another line of investigation that has produced interesting results. High-intensity electromagnetic fields interact with the vacuum in ways that become significant only at extreme field strengths. When electric or magnetic fields reach sufficiently high values, they begin to affect the vacuum itself, altering its properties in measurable ways. One predicted effect is vacuum birefringence, a phenomenon where extremely strong magnetic fields cause the vacuum to behave like a crystal, bending different polarizations of light differently. This effect was predicted decades ago and finally observed in 2017 in the extreme magnetic field of a neutron star. The observation confirmed that the vacuum responds to fields. It is not inert. It has properties that fields can modify. This is consistent with quantum field theory, but actually seeing the effect demonstrated that theory matches reality. If fields can modify vacuum properties, the question becomes how much modification is possible and what effects might be achievable. The neutron star observations involved natural fields far stronger than anything we can produce artificially. But laboratory fields are improving. Laser technology advances steadily, producing ever more intense pulses. Some researchers have proposed that sufficiently intense laser pulses, focused to extreme intensities, might produce measurable effects on space-time geometry. The connection between electromagnetic fields and space-time curvature is well established through general relativity. Einstein's equations show that all forms of energy contribute to curvature, including electromagnetic field energy. At ordinary field strengths, the curvature effects are utterly negligible. But at extreme field strengths, perhaps achievable with advanced lasers, the effects might become detectable. Detection would not produce a warp bubble, but it would confirm that deliberate space-time manipulation is possible in principle. This research direction is in early stages. The required field intensities push the limits of current technology. The predicted effects are tiny even at maximum achievable intensities, but experiments are underway and results are beginning to appear. The connection to warp physics is indirect but real. Warp drive requires space-time manipulation. Any demonstration that space-time can be deliberately manipulated at any scale validates the theoretical framework and suggests that larger-scale manipulation might be achievable with appropriate technology. Let us examine the theoretical side more carefully. The equations of general relativity describe how space-time geometry relates to the distribution of matter and energy. Given a distribution of mass and energy, you can calculate the resulting space-time curvature. Given a desired space-time geometry, you can in principle calculate what distribution of matter and energy would produce it. This reverse calculation is what Alcubierre performed in 1994. He started with the geometry he wanted. a bubble of flat space that moves faster than light, and calculated what energy distribution would create it. The answer was a shell of negative energy density surrounding the flat region. The same approach has been applied to other proposed warp geometries. Different bubble shapes, different velocity profiles, different transition regions all lead to different energy requirements. By exploring the space of possible geometries, researchers have found configurations that require significantly less energy than Alcubierre's original design. One important refinement involves the thickness of the bubble wall. Alcubierre assumed a very thin wall, which turns out to require more energy. Thicker walls with more gradual transitions between normal space and distorted space require less energy. The trade-off is that thicker walls mean larger bubbles for the same interior volume, but the energy savings can be substantial. Another refinement involves the shape of the bubble. Spherical bubbles are mathematically simple, but not necessarily optimal. Ellipsoidal or more complex shapes might achieve the same effective velocity with different energy configurations. Some research suggests that certain asymmetric shapes could be significantly more efficient. A third refinement involves the velocity profile. A bubble moving at constant velocity has different energy requirements than one that is accelerating or decelerating. Understanding how to control bubble velocity efficiently is important for practical applications, since any real journey would involve starting, stopping, and possibly maneuvering. These refinements collectively have reduced energy estimates by many orders of magnitude. What once required more energy than the observable universe might now require only astronomical amounts, perhaps the energy equivalent of a planet's mass or a star's mass. Still far beyond current capability, but no longer obviously forbidden, the theoretical work continues. Each refinement suggests further refinements. The space of possible warp geometries is vast, and exploration has only begun. There is another theoretical direction that has generated excitement in recent years. This involves the possibility that warp-like effects might not require negative energy at all. The original Alcubierre geometry required negative energy because of how it distorted space-time. The compression in front of the bubble and expansion behind created a specific pattern of curvature that could only be produced by negative energy density. But other geometries might achieve similar effects differently. By using moving distributions of positive energy arranged in specific patterns, it might be possible to create space-time distortions that produce effective motion without any negative energy. The mathematics of this approach is more complex. The geometries are not as clean as Alcubierre's original design, but several researchers have shown that self-consistent solutions exist that use only positive energy. The catch is that the positive energy requirements remain enormous. You would need to move huge amounts of mass energy in precisely coordinated patterns to create the desired space-time effects. The engineering challenges are different from those of negative energy approaches, but they are not obviously smaller. Still, eliminating the need for negative energy is conceptually significant. Negative energy has an air of impossibility about it, a sense that you are asking nature for something it does not want to provide. Positive energy is ordinary. We know how to produce it, contain it, move it. The engineering might be prohibitively difficult, but it does not require fundamentally new physics. This distinction matters for how we think about the prospect of warp drive. If warp drive requires negative energy, we might face fundamental barriers that no amount of engineering can overcome. If it requires only positive energy in challenging configurations, the barriers are practical rather than fundamental. Practical barriers can be overcome. They respond to ingenuity and resources. They shrink as technology advances. A barrier that seems insurmountable today might become manageable in a century or a millennium. Let us consider some of the engineering challenges that would face any practical warp drive, regardless of the specific geometry chosen. The most obvious challenge is energy generation and storage. Even optimized warp geometries require enormous amounts of energy. Where does this energy come from? How is it stored until needed? How is it released in the precise configurations required? For negative energy approaches, the challenge is even more fundamental. We can create negative energy density in tiny regions using Casimir-like effects. But scaling this up to volumes that could contain a spacecraft is beyond any current understanding. The physics that produces negative energy at nanometer scales might not extend to larger scales at all. For positive energy approaches, the challenges are more familiar, but still severe. Concentrating planet-scale energies into manageable volumes is not something we know how to do. The energy densities involved would exceed anything in current engineering by many orders of magnitude. Exotic energy sources might help. Antimatter annihilation releases enormous energy per unit mass, but we can only produce antimatter in tiny quantities at enormous cost. Fusion promises high energy density, but controlled fusion remains technically challenging. Some speculative sources, like vacuum energy extraction or dark energy manipulation, might provide the needed energy if the underlying physics permits. But we do not understand these well enough to assess feasibility. Another engineering challenge involves creating the required space-time distortion, even assuming adequate energy. For negative energy approaches, you would need to configure the negative energy density in a precise shell around the bubble interior. The shell must maintain its shape and position throughout the journey. Any asymmetry or fluctuation could destabilize the bubble or send it off course. For positive energy approaches, you would need to coordinate the motion of massive amounts of energy in precise patterns. The timing and positioning would need to be exact. Even small errors might prevent the desired space-time geometry from forming. Control systems for such precision do not currently exist. The tolerances involved are far beyond current engineering. This is not an insurmountable obstacle, but it represents a significant research and development challenge. Stability is another concern. Some theoretical analyses suggest that warp bubbles might be inherently unstable. Small perturbations might grow exponentially, causing the bubble to collapse or fly apart. If this is the case, maintaining a bubble for the duration of an interstellar journey might be impossible. Other analyses suggest that certain geometries are stable, that the bubble would naturally maintain its shape against perturbations. The disagreement reflects incomplete understanding of the physics involved. More detailed calculations, possibly requiring numerical simulations rather than analytical methods, would be needed to resolve the question. Even if stable geometries exist, maintaining stability during maneuvers might be challenging. Starting and stopping the bubble, changing its direction, accelerating or decelerating, all represent perturbations to the system. Understanding how to make these changes without destabilizing the bubble is an unsolved problem. Interaction with the external environment poses additional challenges. Interstellar space is not perfectly empty. It contains thin gas, mostly hydrogen, along with dust particles and occasional larger objects. A warp bubble moving through this medium would interact with it in ways that are not fully understood. Some analyses suggest that matter encountered during flight would accumulate at the bubble boundary, building up in front of the moving distortion. When the bubble stops, this accumulated matter might be released as a burst of high-energy particles, potentially dangerous to anything in the vicinity. Other analyses suggest different outcomes depending on the specific geometry and velocity of the bubble. The physics of the bubble boundary, where space-time distortion is most extreme, is complex and not well characterized. Navigation represents another set of challenges. How do you determine where you are during a warp journey? The bubble interior is flat space, indistinguishable from any other flat region. The external universe is distorted and moving relative to the bubble. Traditional navigation methods assume that you are moving through a fixed background, not that the background itself is in motion. New navigation techniques would need to be developed. These might involve tracking external reference points through the distorted bubble wall, using gravitational wave signals as position markers, or other methods not yet conceived. Communication presents similar difficulties. How do you send or receive signals from inside a moving warp bubble? The bubble wall represents a region of extreme space-time distortion. Signals entering or leaving would be affected in ways that might scramble their content or prevent transmission entirely. For a vessel in warp transit, communication with the external universe might be impossible. The journey would be conducted in isolation, with no ability to receive updates or send reports until the bubble stops. These engineering challenges are severe but not necessarily fatal. History contains many examples of problems that seemed insurmountable but yielded to determined effort. The challenges represent work to be done, not proof that the goal is impossible. Let us turn to a different aspect of the warp drive question: the implications for our understanding of physics itself. General relativity permits warp geometries. This is established. But general relativity is known to be incomplete. It does not account for quantum effects, which become significant at very small scales and very high energies. A complete theory of physics, which we do not yet possess, would merge general relativity with quantum mechanics into a unified framework called quantum gravity. We do not have a fully developed theory of quantum gravity. String theory, loop quantum gravity, and other approaches each have adherents, but none has been confirmed experimentally. The regime where quantum gravity effects become important is so far from accessible energies that direct tests are extremely difficult. This matters for warp drive, because the bubble wall involves extreme space-time curvature. In the transition region between flat interior and distorted exterior, curvatures become very large. Quantum effects might be significant in this region. A full understanding of warp physics might require quantum gravity. This cuts both ways. On one hand, quantum gravity might introduce constraints that forbid warp geometries. Effects we cannot currently calculate might prevent bubbles from forming or maintaining their shape. The apparent permission from classical general relativity might be overridden by quantum corrections. On the other hand, quantum gravity might provide new mechanisms for space-time manipulation. It might reveal that the vacuum has structure we currently miss, structure that could be exploited for propulsion. It might show that negative energy is more accessible than classical calculations suggest, or that entirely different approaches to FTL travel exist. We simply do not know. Until quantum gravity is better understood, this fundamental uncertainty will persist. Some researchers view this uncertainty optimistically. They note that quantum mechanics has frequently expanded possibilities rather than constraining them. The quantum world is stranger and richer than the classical world, containing phenomena like entanglement and superposition that have no classical counterpart. Quantum gravity might similarly expand possibilities in ways we cannot currently anticipate. Others are more cautious. They note that quantum mechanics also introduces constraints, like the uncertainty principle, that prevent certain classical possibilities. Quantum gravity might similarly constrain classical general relativity, forbidding configurations that the classical equations permit. Both perspectives are reasonable, given current knowledge. The question will be resolved only by developing better theory and finding ways to test it. This connection to fundamental physics is one reason why warp drive research attracts interest beyond its practical implications. Even if warp drive never becomes practical, the research program pushes against the boundaries of known physics. It asks questions that illuminate the deep structure of space-time. It motivates theoretical work that has value regardless of whether the practical goal is achieved. Physics often advances through the pursuit of seemingly impossible goals. Attempts to build perpetual motion machines, while ultimately unsuccessful, clarified thermodynamics. Attempts to measure absolute motion, while showing that such motion does not exist, led to relativity. The pursuit of warp drive, even if it fails, might similarly yield insights that advance physics in unexpected directions. Let us consider the historical context more carefully. The relationship between theoretical possibility and practical achievement has varied dramatically across different technologies. Some theoretical possibilities were realized quickly once the principles were understood. Others took much longer. Some remain unrealized despite long effort. Nuclear energy moved from theoretical prediction to practical application in less than 50 years. Fission was understood in the late 1930s, and nuclear power plants were operating by the 1950s. The theoretical possibility translated rapidly into engineering reality. Controlled fusion has followed a different path. The physics has been understood since the 1950s, but practical fusion power remains elusive 70 years later. The engineering challenges have proven far more stubborn than early optimists expected. Every decade brings predictions that fusion is 20 years away, and the prediction keeps proving wrong. Flight was achieved remarkably quickly once the underlying principles were clarified. The Wright brothers succeeded within years of understanding how lift and control actually work. Within decades, aviation had transformed transportation. Within a century, humans had walked on the moon. Space travel followed a similar pattern once rocket science matured. From the first successful liquid-fueled rockets in the 1920s to orbit in 1957 to the moon landing in 1969, the pace of progress was extraordinary. Other technologies have advanced more slowly. Artificial intelligence was predicted for decades before making significant practical progress. Room temperature superconductivity remains elusive despite enormous effort. Life extension has advanced incrementally rather than dramatically, despite centuries of aspiration. Which category will warp drive fall into? We cannot know in advance. The technology might prove achievable sooner than current pessimism suggests, or it might join the long-delayed or permanently impossible categories. What we can observe is that the factors predicting rapid realization include well-understood physics, manageable engineering challenges, and strong motivation for development. Warp drive currently fails on the first two criteria and partially meets the third. The physics is not fully understood. The engineering challenges are severe, but motivation exists, at least among a small community of researchers and enthusiasts. If the physics becomes better understood, if breakthrough experiments clarify what is possible, motivation could increase dramatically. A demonstration that space-time manipulation is achievable, even at microscopic scales, would attract resources and talent. The timeline could compress. Alternatively, further research might clarify that fundamental barriers exist. Conclusive evidence that warp geometries are forbidden by physics we do not yet understand would redirect effort elsewhere. This outcome would be disappointing, but would also represent progress, closing a path so that resources can focus on more promising directions. Either outcome would be valuable. The current uncertainty, while intellectually uncomfortable, will not persist indefinitely. Research continues and answers will emerge. Let us examine the social and institutional context of warp drive research. Science does not happen in a vacuum. It requires funding, institutional support, trained researchers, and publication venues. The sociology of science shapes what gets studied and what gets ignored. Warp drive research occupies an unusual position in this landscape. It is not quite mainstream physics, but it is not quite fringe either. The mathematics is rigorous. The papers appear in respected journals. But the topic is sufficiently speculative that few physics departments would dedicate significant resources to it. This marginal status has consequences. Funding is limited. Most researchers work on warp physics as a side interest rather than a primary focus. Graduate students are rarely advised to pursue the topic, since career prospects are uncertain. The community remains small, despite growing interest. Private funding has partially filled the gap. Organizations supported by wealthy individuals with long-time horizons have provided resources for research that government agencies cannot easily justify. This funding model has limitations, depending on the continued interest and resources of a few patrons. But it has enabled work that would not otherwise occur. International collaboration happens informally. Researchers communicate through published papers, conference presentations, and direct correspondence. The community is small enough that most active participants know each other. This intimacy allows rapid circulation of new ideas, but also limits the total effort devoted to the field. Public interest in warp drive exceeds scientific investment by a wide margin. Science fiction has made faster-than-light travel a cultural touchstone. Popular articles about warp drive research attract large audiences. This interest creates opportunities for science communication, but also risks generating unrealistic expectations. Managing expectations is a delicate task. Researchers want to convey the genuine excitement of the field, the sense that something important might be possible. But they also need to be honest about the enormous obstacles and uncertain timeline. Overpromising leads to disappointment and skepticism when rapid progress fails to materialize. The current moment is interesting, because several developments have converged to increase attention on the field. Theoretical papers, reducing energy requirements, anomalous experimental results that might hint at new physics, improved computational tools for exploring warp geometries, and growing private funding have all contributed to a sense of momentum. Whether this momentum leads to genuine breakthroughs or dissipates as obstacles prove stubborn remains to be seen. The next decade will likely be significant for determining the field's trajectory. Let us consider what success would mean. Not in the far future when interstellar travel might become routine, but in the nearer term when initial demonstrations might occur. The most important near-term goal is demonstrating that space-time can be deliberately manipulated at any scale. Even a microscopic effect, far too small for practical propulsion, would be transformative. It would confirm that the theoretical framework is correct, that space-time manipulation is possible, that the path toward larger-scale effects is worth pursuing. Such a demonstration would likely involve detecting tiny space-time distortions produced by laboratory apparatus. The effects would be at the edge of detectability, requiring extraordinarily sensitive instruments. The signal would need to be distinguished from noise and potential artifacts. Confirmation would require replication by independent groups. This process would take years, even after the initial detection. Science proceeds cautiously, especially for extraordinary claims. But if the effect were confirmed, the implications would ripple outward. Funding would increase dramatically. Agencies that currently cannot justify warp research would find themselves under pressure to participate. Private investment would multiply. Talent would flow into the field as career prospects improved. Theoretical work would intensify. Knowing that space-time manipulation is possible would focus effort on understanding how to scale it. New geometries would be proposed, analyzed, and tested. The space of possibilities would be explored much more thoroughly. Engineering analysis would begin in earnest. Questions about energy requirements, materials, control systems, and safety would shift from academic speculation to practical concern. The transition from physics to engineering, while still distant, would begin to be mapped. Public interest would explode. Media coverage would be intense. The cultural impact of knowing that faster-than-light travel might be achievable within some horizon would be significant. Human civilization's self-conception as potentially interstellar would strengthen. All of this from a microscopic laboratory demonstration that cannot actually transport anything. The demonstration matters not for what it accomplishes directly, but for what it proves possible. Let us think about the longer-term trajectory, assuming initial demonstrations succeed. Scaling from microscopic effects to macroscopic effects is never straightforward. Physics sometimes behaves differently at different scales. Effects that work at small scales might fail at large scales for reasons that are not apparent until you try. History contains many examples of technologies that worked beautifully in the laboratory, but failed to scale for practical use. For warp physics, scaling challenges include energy requirements, material properties, stability, and control. Each of these might present obstacles that only become apparent as scale increases. Energy requirements are the most obvious concern. Laboratory demonstrations might require only manageable energies. Spacecraft-sized bubbles would require many orders of magnitude more. Where this energy comes from, how it is stored, how it is converted to the required form, are all challenges that grow with scale. Material challenges relate to the conditions inside a warp bubble generator. Whatever form that might take, the fields and energies involved would stress materials in ways that current technology cannot handle. New materials with extreme properties might be required, materials that might be possible in principle, but far from current capability. Stability is another scaling concern. A microscopic distortion might be stable by default, too small for destabilizing effects to grow. A larger distortion might require active stabilization, feedback systems that detect and correct deviations before they grow. Designing such systems requires understanding the physics in detail that current theory might not provide. Control becomes more complex at larger scales. Steering a microscopic distortion is conceptually simple, even if technically difficult. Steering a spacecraft-sized bubble through interstellar space, avoiding obstacles, navigating to a destination, requires systems far more sophisticated. Each of these scaling challenges might be surmountable, or one or more might prove fundamental. We will not know until we try. The history of technology suggests that most scaling challenges eventually yield to persistent effort, but some do not. There is no guarantee. Assuming scaling succeeds, the development trajectory might resemble other transformative technologies. Initial demonstrations would be followed by gradual improvement. First-generation devices would be crude, expensive, and limited. Second-generation devices would be better. The cycle would continue, with each generation building on lessons from the last. Timescales for this development could range from decades to centuries depending on the difficulty of the challenges and the resources devoted to addressing them. Transformative technologies have varied enormously in their development times. Aviation went from first flight to routine commercial service in about 50 years. Space travel went from first orbit to moon landing in 12 years, but then stalled for decades. Nuclear fusion has been under development for 70 years without achieving practical power generation. Warp drive development, if it proves possible, might follow any of these patterns. It might proceed rapidly once the initial demonstrations occur, driven by intense interest and massive investment. Or it might proceed slowly, as obstacle after obstacle proves more difficult than expected. Or it might proceed in fits and starts, with periods of rapid progress separated by periods of stagnation. Prediction is impossible. We can only observe that transformative technologies do get developed, that seemingly insurmountable obstacles do get overcome, and that human persistence and ingenuity have repeatedly achieved what earlier generations considered impossible. Let us consider the broader context in which warp drive development would occur. Human civilization faces challenges on multiple fronts. Climate change threatens environmental stability. Political conflicts risk devastating wars. Technological disruption transforms economies faster than social systems can adapt. Existential risks from artificial intelligence, bioengineered pathogens, and other sources demand attention. In this context, warp drive research might seem like a luxury, a diversion of resources from more pressing concerns. Why pursue interstellar travel when we have not solved problems on Earth? This critique has some validity. Resources are finite, attention is limited. Pursuing distant goals can distract from immediate needs. But there is another perspective. Humanity's future depends on capabilities that are developed over long timescales. Challenges that seem distant today might become urgent tomorrow. Technologies that seem impractical now might become essential later. Interstellar travel capability represents an extreme form of resilience. A civilization confined to one planet is vulnerable to extinction from numerous causes. A civilization spread across multiple star systems is much more robust. Even if warp drive lies far in the future, beginning the research now increases the chance of eventual success. Moreover, research on fundamental physics often produces unexpected benefits. Technologies developed for one purpose find applications elsewhere. Understanding gained in one domain illuminates others. The pursuit of warp drive, even if it never achieves its stated goal, might advance physics and engineering in ways that benefit humanity more broadly. This is not an argument for unlimited investment in speculative research. Resources should be allocated thoughtfully, with attention to both near-term needs and long-term possibilities. But some investment in long-shot technologies is justified, both for the direct benefits, if they succeed, and for the indirect benefits of the research process itself. The current level of warp drive research is modest. It consumes a tiny fraction of global science funding. Increasing this investment modestly would not significantly divert resources from other priorities, while potentially accelerating progress on a technology of enormous importance. Let us examine some specific recent developments in the field. In 2021, a paper by physicist Eric Lentz proposed a new class of warp geometries that might require only positive energy. The geometries are called constant velocity subluminal solitons, complex configurations of positive energy that create self-sustaining space-time waves. These waves could in principle transport a payload without requiring the negative energy that previous warp designs demanded. The energy requirements remain enormous, but eliminating the need for exotic matter represents a conceptual advance. Positive energy is familiar. We know it exists. We know how to produce and manipulate it, at least at scales far below what warp drive would require. Building on familiar physics is more promising than requiring physics we do not understand. In 2022, researchers at DARPA, the U.S. Defense Research Agency, announced funding for warp drive research. The amounts were small by DARPA standards, but the involvement of a major government agency signaled increased institutional legitimacy for the field. DARPA's interest focuses on experimental approaches to detecting space-time manipulation, attempting to move from pure theory toward laboratory science. In 2023, several papers appeared exploring quantum effects in warp geometries. These analyses examined how quantum fields would behave in the extreme curvature of bubble walls. Some results suggested that quantum effects might stabilize certain geometries. Others suggested new instabilities. The work represents progress toward understanding how quantum mechanics and warp physics interact, even though conclusive answers remain elusive. Experimental work has also continued. Multiple groups are pursuing improved measurements of vacuum effects, searching for anomalies that might indicate new physics. The sensitivity of instruments improves steadily. Effects that were undetectable a decade ago are now measurable. Effects that remain below current sensitivity might become accessible with next-generation equipment. None of these developments represents a breakthrough. The field advances incrementally rather than dramatically, but the direction is consistent. Understanding deepens. Possibilities narrow or expand as analysis proceeds. The space of what might be achievable becomes better defined. Let us step back And consider what warp drive would mean for humanity's place in the universe. We currently inhabit one planet, orbiting one star, in a galaxy containing hundreds of billions of stars. Beyond our galaxy lie hundreds of billions of other galaxies. The scale of the universe is beyond human comprehension. Numbers fail to convey it. Analogies collapse under the weight of the distances involved. In this vast cosmos, humanity is isolated. We have visited no other world in person except our own moon. We have sent robotic probes to nearby planets and moons, but even these missions take years and reach only our immediate neighborhood. The stars remain utterly beyond reach. This isolation shapes how we think about ourselves. We are alone, as far as we know. We might be unique. We might be one of many civilizations, but we have no evidence of others and no way to seek them. Our cosmic context is one of profound solitude. Warp drive would change this fundamentally. With the ability to cross interstellar distances in reasonable time frames, humanity could explore the galaxy directly. We could visit other star systems, examine other planets, search for life beyond Earth. The question of whether we are alone could be answered through direct investigation rather than passive listening. Finding other life, even microbial life, would be transformative. It would prove that the origin of life is not unique to Earth, that the universe contains the conditions and processes that generate living things. Finding complex life would be even more significant. Finding intelligent life would be the most important discovery in human history. Even negative results would be informative. Visiting hundreds of star systems and finding no life would suggest that life is rare, that the conditions on Earth that permitted our existence are unusual. This would give us a different understanding of our cosmic significance. The ability to establish permanent settlements beyond Earth would transform humanity from a single planet species to a potentially multi-planet or multi-stellar civilization. This represents resilience against existential risks. If something destroyed Earth, humanity would continue elsewhere. If something destroyed one colony, others would survive. This resilience matters not just for survival, but for what humanity might achieve. A civilization spread across many worlds would have more resources, more perspectives, more opportunities for discovery and creation. The potential for human flourishing would be vastly greater. Of course, spreading across the stars would also spread human conflicts and problems. We would not escape ourselves by traveling to other worlds. Whatever divisions, disputes, and difficulties we experience on Earth would accompany us into space. But we would face those challenges with greater resources and more room for different approaches. The diversity of environments would encourage the diversity of solutions. Over time, separated human communities might develop different ways of organizing society, different technologies, different cultures. This diversity, while potentially fragmenting, would also provide resilience against mistakes. A failed approach in one system would not doom all of humanity. These considerations take us far beyond current capabilities. Warp drive remains speculative. The future I am describing might never arrive. But imagining it clarifies what is at stake, why the research matters, what we might gain or lose depending on how the physics turns out. Let us return to the present and consider what could be done now. The most important near-term activity is continued research, both theoretical and experimental. Theoretical work should continue exploring warp geometries, searching for configurations that minimize requirements and maximize practicality. Experimental work should continue probing vacuum effects, searching for anomalies that might reveal new physics. Funding for this research should modestly increase. The field is understaffed relative to its potential importance. Additional resources would allow more researchers to work on these questions, accelerating the pace of discovery. The amounts involved are small by the standards of major science programs. Institutional support should grow. Universities and research laboratories should be more willing to host warp drive research, recognizing that speculative work can eventually become mainstream science. Career paths for researchers in the field should become more stable, attracting talented people who currently avoid the topic due to professional risk. International collaboration should strengthen. While current informal networks function, more formal collaboration could accelerate progress. Shared experimental facilities, coordinated theoretical programs, and joint training initiatives would all help. Public communication should continue, with appropriate calibration of expectations. Interest in warp drive is high, but understanding of the actual state of research is often limited. Clear communication about what is known, what is uncertain, and what remains unknown would help create realistic expectations while maintaining enthusiasm. These steps would not guarantee success. The physics might simply not permit what we hope, but they would give the field its best chance of making progress, of answering the fundamental questions that determine whether warp drive is possible. Let us consider one final aspect of the warp drive question: the philosophical dimension. Humans have always been explorers. From the first migrations out of Africa, to the settlement of every continent, to the voyages of discovery, to the exploration of space, we push outward. This drive is deep in our nature, perhaps selected by evolution, perhaps arising from our unique cognitive capabilities. We want to know what lies beyond the horizon. The stars represent the ultimate horizon. Everything else we might explore exists within the solar system, a single star's neighborhood. The galaxy, containing hundreds of billions of stars, stretches beyond. The universe, containing hundreds of billions of galaxies, stretches beyond that. The scale of what we cannot reach dwarfs the scale of what we can. If warp drive proves impossible, we might learn to accept this limitation. Humanity could flourish within the solar system, building civilizations across planets and moons, finding meaning and purpose in what is accessible. We are adaptable. We adjust our ambitions to our capabilities, but something would be lost. The knowledge that the stars are forever beyond reach would constrain human aspiration in a way that nothing else has. Every previous limit has either been transcended or remains theoretically surmountable. The light speed barrier, if truly insurmountable, would be different. It would close the cosmic horizon permanently. If warp drive proves possible, the horizon opens. Perhaps not immediately, perhaps not for centuries, but eventually, someday, humans would walk on worlds orbiting other stars. We would look up at alien skies and see unfamiliar constellations. We would know that the universe is our home, not our prison. This possibility is why the research matters. Not because we expect rapid practical applications, not because we need interstellar travel to solve immediate problems, but because the question of whether the stars are reachable is one of the most profound questions humanity can ask. We are asking it now. The research continues. The answer will come. Perhaps the answer is no. Perhaps physics has set a hard limit that no cleverness can circumvent. We would learn to live with that knowledge. Perhaps the answer is yes. Perhaps the equations that hint at possibility will prove correct. Perhaps some future generation will board a vessel that moves not through space but with space. Perhaps they will arrive at a destination light years away within their own lifetimes. We cannot know yet which answer awaits. We can only continue the work, follow the evidence, refine the theories, conduct the experiments. The answer will reveal itself in time. The universe is vast, ancient, and mostly empty. On one small planet, orbiting one ordinary star, creatures have evolved who can ask whether they might someday cross the void. The question itself is remarkable. That we can even formulate it, that we can do mathematics precise enough to analyze it, that we can build experiments sensitive enough to probe it. These are achievements worth celebrating regardless of the outcome. The stars burn in their billions across the night sky. They have burned for billions of years before us, and will burn for billions of years after, whether we ever reach them, whether any of our descendants ever stand on worlds circling distant suns. They will continue their ancient processes, indifferent to our striving. But we are not indifferent. We look up and wonder. We calculate and experiment. We dream and work. This is what humans do. This is what makes us human. The research continues. The questions remain open. The future remains unwritten. And somewhere in the equations, in the experiments, in the dreams, the answer waits. We will find it eventually. We always do. The stars are calling. Whether we can answer is the question. The search for that answer is the work. And the work, whatever it reveals, is worthy.